Quantum mechanics has shown, for decades, that smaller particles can behave in ways that challenge common sense. But what happens when what is tested is not electrons or individual atoms, but whole clusters of thousands of metal atoms? The answer just came from a Vienna laboratory. Yes, those macroscopic structures can also enter a state of quantum overlap, as if they existed in several places at the same time. If you're interested in quantum physics and its amazing discoveries, subscribe to our channel and like this video. Don't miss the updates on the latest developments in this fascinating field of study. A team of physicists has managed to place sodium metal nanoparticles made up of to 10,000 atoms in a state known as Schrödinger's cat. In that state, each particle does not have a fixed location, but behaves as if it were in more than one place at a time. This finding represents one of the most significant advances in seeking to understand how far quantum logic can be stretched. The work was carried out by researchers from the University of Vienna and Duisburg-Essen University, and marks a milestone in the exploration of so-called quantum macroscopicity. Until now, quantum interference experiments had been carried out with simple atoms and molecules, but this time large-mass metal nanoparticles were used. Scientists used a matter interferometry technique in which clusters cool, align, and then pass through 3 ultraviolet laser-generated grids. The result was a visible interference pattern that can only be explained if particles behave like quantum waves. The key to the experiment is not only in the size of the particles, but also in the distance they travel without being measured. During that journey, their position is not fixed, which implies a delocalization that exceeds more than one order of magnitude the particle's own size. The term Schrödinger cat state describes situations in which a system can be found in 2 mutually exclusive states at the same time. In this case, sodium clusters were simultaneously here and there in spatial terms. The most striking thing is that these quantum states did not collapse during the experiment. Interference remained visible, which reinforces the validity of the quantum model, even for large objects. The quantum world extends beyond electrons and small molecules. To achieve this result, the team developed an experimental platform called Muscle. Their sodium clusters are generated in an aggregation chamber, and 77 kelvins are cooled before being analyzed in a Talbot-Lowe interferometer. One of the most outstanding contributions of the study is the reached value of quantum macroscopicity, which quantifies how large or classical a system is in quantum state. This experiment obtained a value of mu equals 15.5, surpassing the previous record. The experiment not only shows that quantum laws apply to larger objects than was believed, but also opens the door to new research with complex materials. In addition, the interferometer has practical applications in nanotechnology and other areas.